Thank you. Hi everyone, my name is Ilias. I work as an embedded engineer, and in the next 15 minutes I'll tell you a story of how I was able to make a small contribution to the public research by reproducing the vulnerability related to Bluetooth on Raspberry Pi, and why patching it is not trivial. Before we start though, please raise your hand if you use Bluetooth on a regular basis, whether it's for work purposes or not. Well, pretty much a similar percentage of people who didn't vote Tories or Reform this year. To be honest, it shouldn't come as a surprise, because Bluetooth is everywhere, it surrounds us. According to Bluetooth Standards Organization, only in 2023, over 5 billion devices were shipped worldwide, starting from laptops and smartphones to cars, key fobs, and hell, I haven't seen toasters with Bluetooth. And it's not surprised why Bluetooth is pretty much popular. It's essentially a short-range wireless protocol that works on high radio frequency, and it allows to exchange the data between devices, and in some cases you can even create the network of these devices. For example, that's what Bluetooth Mesh is for. But obviously, over 20 years since Bluetooth exists, it's not bulletproof, and hundreds of vulnerabilities were being found. And one of these vulnerabilities was Braktooth. So essentially in 2021, a group of researchers from Singapore discovered a series of vulnerabilities in the commercial Bluetooth stack implementation of within System-on-Chips, particularly targeted against Link Manager protocol. In short, Link Manager protocol is essentially a protocol that is responsible for negotiating all the connection stages between two devices. And because the chipsets that were found vulnerable included big names such as Intel or Qualcomm and others, it meant that billions of devices were being vulnerable to this. But researchers haven't tested Raspberry Pis, and because my main work involves working on Raspberry Pis, and at that time the proof of concept wasn't being publicly released for disclosure reasons, I asked for proof of concept, and happily they provided to me. So essentially the attack model was pretty much simple. I have a Raspberry Pi 4. It was running Ubuntu 20 LTS with latest updates. Again, it was back in 2021. And it is being connected to the DVOOM speaker. Just simply connected to the DVOOM speaker, and meanwhile I, as an imposter, I should try to disrupt the Bluetooth connection between these two devices. Essentially, this is how it looked like in real life. So first things first, obviously I needed to set up the connection between Raspberry Pi and the DVOOM speaker. If anyone's surprised why I'm using command line, is because first of all, I was running an Ubuntu LTS without UI on Raspberry Pi, and secondly, it is easier for me to explain what's actually happening behind the scenes. So the pairing has been established. Obviously, it uses the pin code, and as you can see, the command profile has changed to Timebox Evo Audio, which was the name of my DVOOM speaker, meaning that it has paired and connected. Raspberry Pi has paired and connected to it. Now, Cypress has 4 vulnerabilities of 16 attributed to it. I'll focus on the one that I used, which is invalid max slot type, LMP invalid max slot type. Essentially, Bluetooth has 5 types of logical transport communications, and one of them is asynchronous connectionless, stands for ACL. Essentially, ACL is used for exchanging the data where you need to use as much bandwidth as possible. For example, if you connect your phone or desktop to the remote speaker or smart TV and you want to play a song or a video, usually ACL is used for that purpose. The problem is ACL by its design is not designed for the broadcast packets. There is a specific logical transport protocol for this. And essentially, what the exploit is, the logic of the exploit is that if you malform the packet, one of the fields in a packet, particularly LT address, which is logical transport address. Essentially, it means that usually LT address is generated randomly for each connection. But if you set it to 0, and 0 was reserved for the broadcast packets, and send it as an ACL, which is not designed as a broadcast packets, essentially it should crash the device. It is, funny enough, it is outlined, it is strictly forbidden to do this per Bluetooth specification, but apparently the vendors haven't expected this, so basically, which is why it was supposed to crash the Bluetooth connection between these two devices. So basically, this is the output of me running an exploit, which is pretty much standard and nothing much interesting stuff there is happening. Then I decided to look at the Raspberry Pi and see how it's behaving. And I already had the first sign of hope when I saw the agent unregistered line. Now the Linux desktop uses on operating system level, Linux uses Blues as a Bluetooth stack, and essentially it's Blues who is responsible for creating a Bluetooth service within the Raspberry Pi. And agent object is a high-level DBus object that is responsible for that is basically acts like a supervisor for pairing and connection authentication authorization between two devices. And basically, when for no other reason it says that agent unregistered, essentially it means it doesn't know what's happening. I'm giving up. I'm just living out here. And then I saw something that I actually didn't expect. Not only was I able to disrupt the Bluetooth connection, as you can see by command profile, which is reverted back to Bluetooth, but I actually managed to crash Bluetooth service, and which is seen by the line controller, then MAC address of my Raspberry Pi, and the Ubuntu name, which is Ubuntu was the name of my Bluetooth name of my device, and essentially forced to restart and register back the agent. And considering this was my second attempt at running this exploit, first time I tried with another exploit, not only it didn't work, but I managed to find a bug in POC, in proof of concept. I was pleasantly surprised by this. Now, some of you might think, well, that was in 2021. Surely that has been fixed by Cypress. And credit where it's due, Cypress was one of the vendors who quickly fixed this vulnerability in their code. But one thing is fixing the code. Another thing is distributing it. Distributing the fix, I mean. And that's where the problems begin. Now, for upgrades, so basically Cypress System-on-Chip, for Cypress System-on-Chips, the firmware is being flashed at the manufacturing stage to the read-only memory, which means that essentially you make the firmware immutable to directly flash and update it. However, but obviously you need to update the firmware. For example, when security fixes you need to apply security fixes or non-security fixes. And for that, they use something called patchram. Patchram essentially is based on the flash patch unit, which is a part of ARM architecture. And imagine if you're trying to debug a problem and you're putting a breakpoint in it. Essentially, patchram is that breakpoint. It contains the specific value, it contains the address that needs to be targeted, and then it will override with new values within the firmware that is stored in read-only memory. You can find, basically these patchram slots are being distributed as HCD files by operating system updates. So basically if you run, for example, sudo apt update or upgrade, HCD files are being applied through the repositories. But the problem is, there isn't infinite number of these patchram slots. This first item in this patchram slot indicates the index slot of this patchram. And because it's 1 byte, there cannot be more than 256 slots. But in reality, Raspberry Pi has only 128 slots of these patches, of these patchram slots. And that's where the problems begin, because essentially Cypress, it is completely up to Cypress to decide which vulnerabilities to fix and which are not to fix, for one simple reason. So let me give you an example. Raspberry Pi 4 was released in 2018. In just 1 year, all slots except for one were reserved. To make matters worse, it was successful. It turns out that the compilation date of the firmware that has been stored in stored in read-only memory was in 2014. So by the time the Raspberry Pi 4 was released, they already had to apply 4 years worth of fixes. And by today, they have to apply 10 years of fixes. And basically they decide which, and because 128 slots is not enough, it means that it is, essentially their response. They decide, which, fix to take out and which to slot in. Now, question is how to mitigate it. If you think that upgrading to Raspberry Pi 5 would resolve the issue, abandon or hold because they use the same chip as Raspberry Pi 4. So basically, on that level, the problem still exists. First, so basically, there are, so in terms of, to mitigate it, it depends on whether you use Bluetooth on Raspberry Pi or not. If you don't use, I suggest to turn off the adapter and turn off service entirely so that you won't be able, so that you'll close that loop. If you use Bluetooth on Raspberry Pi, for example, if you run Home Assistant with it, within it, then there are two options with it. Either you use the external Bluetooth dongle. For example, TP-Link sells the dongle for 40 quid, I believe, and it's the one I tested it actually. Or if you don't want to use dongle, you have to keep the OS updated and pray to all gods the Cypress has patched this vulnerability. Now, to make it a small off-top, because Broadcom is owned by Cypress and some chips by Broadcom are used in smartphones and laptops, it means that the problem with Braktooth and with the firmware upgrade process is basically some laptops and smartphones also fall into that category, particularly iPhones and MacBooks, and actually it was proved. So on iPhones, it was several researchers were able to reproduce it, and some others are Samsung Galaxy smartphones. In fact, Samsung Galaxy reported to the research team, confirming that they are vulnerable as well. So if anyone's here owning Samsung Galaxy, you'll be warned. Last but not least, if you want to read more about the Braktooth, about Cypress upgrade process, about how iPhones were being able to exploit, you can check out those links. Don't worry, I'll publish the slides on my website. You can download them by latest by tomorrow. Few words of thanks are in order. First of all, I want to thank my employer for giving me a few days to research this problem on Raspberry Pis. Special thanks also to Viper Bedi, who was one of the researchers behind Braktooth and who was able, and with whom I've kept contact, and he was able to confirm that Raspberry Pis are vulnerable. Another special thanks to Iska Klassen, who pointed out to me the issue with Cypress upgrade process. In fact, she was one of the researchers behind it. And in general, she's an excellent expert on wireless communications, especially when it comes to Apple devices. Very big thanks to my mentor, Aoyama-san. I appreciate every feedback and the advice that you've given. Thank you very much. Lastly, I want to thank each and every one of you for coming, and I hope you enjoyed this talk. If you want to reach out to me, you can scan the QR code, which leads to my website with socials and contact details. And if you have any questions, I'll do my best to answer. Thank you.
We have a few questions. Are you okay? I'll start at the front and work back.
Thank you. Is Bluetooth disabled by default in Raspberry Pis, or
it is not?
So it's by default on, and
it is by default enabled. You essentially can. I would suggest to actually mask the entire service if you don't want to use Bluetooth in general, so that it will not be, so that you won't be able to. No one will be able to hijack into it in any way.
Right, thank you.
Down the back there.
Thanks. So what's kind of the main effect of this vulnerability? Like, what does this allow a potential attacker to do?
For example, and this is something that researchers did, is that if you have a noisy neighborhood who's turning music loud enough, and you want to shut off that idiot's speaker, then you can certainly make it turn off. And in fact, when I did the attack and it was able to crash the service, I was able to reconnect to that device for 5 minutes. So you have 5 minutes of silence, basically.
Why did you patch it? Why did you get it patched? It sounds brilliant.
Why didn't it get patched?
It sounds useful.
Yeah.
Any other questions? No? In that case, huge thanks to Ilias.
Thank you.